In this segment, we will develop a second method that will work for linear circuits. This method is called the Thevenin method, and it's a complementary method, the Norton method. So in order to develop this method for linear circuits, suppose you have some arbitrary network N. And let's say in this arbitrary network, you have a whole bunch of resistors, you have a whole bunch of voltage sources, VM, a whole bunch of sources, current sources as well. Okay, so you have a bunch of voltage sources, and these are all independent voltage sources for now, V1, V2, V3, all the way through Vm. You have a whole bunch of current sources, I1, I2, I3, all the way through to In. Suppose I am interested in applying some kind of excitation due to an external source, current source with current I, and let us say that all I care to do is to determine the voltage V. Okay, so the setup here is I have an arbitrary network N with a ton of resistors and voltage sources and current sources, all independent. And I apply an external excitation, it's a current I, and just assume that all I want to do is to determine the voltage V. Okay, assume that I don't care about any internal voltages, VI, or any internal currents, IJ, and so on. Let's say I don't care about any of those internal currents. All I care about is the voltage V. So in a situation like this, where you care about some voltage or current at some point, you can use the property of linearity and the resulting superposition property to develop an extremely powerful method to get you to your answer very quickly. So in order to develop this method, let me use the superposition technique and try to figure out the voltage V. So the voltage V will be some combination of sources in the circuit. So let's say, for example, I want to figure out the contribution to the voltage V due to the voltage source Vm. What I would then do is I would set I to 0, I would set all the currents I1 through In to 0, and I would set all the voltages V1 through Vm-1 to 0 as well, and just look at the impact on V due to Vm acting alone. So the impact on V due to Vm acting alone. And notice that once all the currents have been turned off and all the other voltages have been turned off, I'm left with a big resistor network, and I'm going to get some multiplier here. Let's label that alpha M. So that will be the result of the source Vm acting alone on the output voltage V. Similarly, I can do the same thing for all the voltages. I can do it for V1 acting alone. I can do it for V2 acting alone, so on and so forth. For each of those voltages, V1, V2, and so on, I get a term that looks like this. I get alpha 1 V1, alpha 2 V2, and so on and so forth, all the way through alpha M Vm. And so what I get is a sum over M of all of these terms. By applying V1 acting alone and V2 acting alone and so on, I get a term alpha 1 V1, alpha 2 V2, and so on. Next, I will move on to the currents. And in this case, supposing I set all the currents save for In, I'm going to set the small I to 0, I'm going to set all the VMs to 0, and I'm going to set all the currents I1 through In-1 to 0. So in that situation, I'm going to get some factor Bn that applies to In. So I get some factor Bn, a beta n that applies to In, and that is the result of In acting alone. Now similarly, I can have I1 acting alone, I2 acting alone, and so on, and for each of them I get a term beta 1 I1 plus beta 2 I2, and so on and so forth, and I sum them all up as well over all n. So with I acting alone, I'm going to set all of the other INs and the VMs to 0 and just have I acting alone, and so therefore I'll get an I, and I'm going to have some multiplier, and in this case, notice that when all the VMs and all the INs are set to 0, I'm just left with a big resistive network here. And so it will look like a big effective resistor looking into this port. And so let me write that down as some R multiplied by the current I. So notice now that the voltage V is a sum of a bunch of components that arise from the voltages acting alone, the currents acting alone, and also the external excitation acting alone. And just recall, how did I get this? How did I get each of these terms? So I got this term by setting this term which sums up all the voltages. I got by setting all the INs to 0 and by setting the external excitation to 0. Similarly, I got the second term here by setting all the voltage sources to 0 and also by setting the external excitation to 0. And finally, this last term, I got that by setting all the currents to 0 and all the voltages to 0. So what we're going to do now is, by using this insight, we're going to build up a new technique. And to give you a preview to that technique, I'm going to show you a trick that will enable you to replace this network N by something very, very simple. In fact, I'm going to show you that we're going to be able to replace that entire network by some voltage source and some resistor acting in series. And this will be able to replace this entire network N for the purpose of computing the voltage V. Okay, so just think of that as a preview of upcoming attractions. So moving on, let's take a look at the equation that we just developed and understand that a little bit more. So if you look at the equation here that we developed, V is some component related to VMs, some component related to INs, and some component related to the external excitation I. So if you look at this term here, if you look at the alpha M term here, that has no units. It has no units because I have a voltage on the left-hand side, and it's multiplying a voltage. Similarly, beta and IN must result in a voltage, and so therefore beta N must have resistance units. And then similarly, R, that is multiplying I, must have resistance units as well. So notice that if you look at the Vn related term and the In related term, then what you see is that together they are independent of the external excitation, and they behave like a voltage. Similarly, if you look at the right hand term here, Ri, that's a resistance multiplied by a current, and of course that also has the resulting voltage units. So let's look at the first part here, the part comprising the VMs and the INs. That behaves like a voltage, and it is independent of external excitation. And so what I'm going to do is I'm going to call it VTH. Okay, and don't worry about why I'm calling it VTH right now, but let's assume that I call it VTH. So that's the first component that is independent of external excitation and behaves like a voltage. Now, if you look at the second component, as I said earlier, the second component clearly depends on the current I. But if you look at the multiplier R, then that is also independent of external excitation and behaves like a resistor. So let us call that RTH. So again, if you look at the term related, the term that gives you V, it will now comprise a portion that we've called VTH, and it has a second component that relates to the external excitation I, but is multiplied by something we call RTH, where the RTH is independent of the external excitation I. So what I've just done is I have written down the excitation as a sum of a voltage here that I decided to call VTH, and I've also said that the second part is RTH times I, and that is equal to the voltage V. So notice V equals VTH plus RTH I. So in other words, if you look at this expression here, as far as the external world is concerned, and again for the purpose of computing the voltage V, our network N is completely indistinguishable from another network. What does that network look like? So this whole network N can be replaced by the following network that I'm going to show you in a quick second. So I have a voltage VTH here, and I have a resistance RTH, and this is my voltage V. And what I've done here is, according to this equation, V equals VTH plus RTHI, I have simply expressed that in circuit form as a little pattern showing a VTH and then with an RTH in series. And this is easy to see that when I is 0, the voltage at the output here is VTH, and then if I have a short circuit where V is 0, then the current through that short circuit will simply be given by VTH divided by RTH. And so this little pattern here can now replace my network N for the purpose of computing V. This network is called the Thevenin equivalent network. And so I can take this network, replace the arbitrary network N with this network, the Thevenin equivalent network, and then I can connect my external excitation I and then compute the voltage V that appears across the terminals. In other words, what I've done is using the Thevenin method, I can take an arbitrary network N, I can figure out a VTH and RTH that relate solely to that network's properties, and then replace that network with VTH and RTH in series, and the series connection is called the Thevenin equivalent network. So you will see this is another pattern. This is called the Thevenin pattern. So in circuits and electronics courses, you will see the Thevenin pattern very often, and in this pattern, you have a voltage source in series with a resistor. And again, it's easy to see that when you have I being 0, then the VTH, the Thevenin voltage VTH, appears at the output terminal as a VTH. And similarly, if you short the terminal pair here, where V is 0, then your current is going to be given by the expression VTH divided by RTH. And since the current is going to be in the direction opposite to this current I, there'll be a negative. But essentially, you can see why this expression V equals VTH plus RTH I directly relates to the Thevenin pattern with the voltage source in series with the resistance.